Okay, good afternoon, everybody. You are welcome to the November 2025 Numerical Analysis Research Cluster Seminar Series. And this afternoon, we'll be, discussing about the numerics of quantum stochastic differential equation and inclusion. But before we start the presentation, I would just like to welcome you for this afternoon's research seminar, and to also encourage us to continue to work in this field and to take advantage of this platform to collaborate and learn and share ideas from our research areas, and also to please help us propagate this platform. Tell your students, your research colleagues, and people, both international and local, about what we do in the numerical analysis research cluster. And if you know any notable person or anybody you would like us to invite to speak to us, you can reach out to us on our email and send us an email. We will try to reach out to the person to speak to us and give us a seminar on his research area. This is a platform mostly created for students, PhD students and master students who are learning the field, and to introduce them to areas and new areas of numerical analysis, so that we don't just find ourselves in some certain areas in numerical analysis which we observed in the country at some point. We are trying to change that narrative by introducing us to new fields and fields where we find that people dread the most. So we are trying to look for mentors and people that can help our students and help early career researchers to have interest in these areas, and also to be able to create or form collaborative teams or research teams or research teams that can also take up projects too. So this afternoon, I'll just ask us to be attentive and take as much as we can from this talk, and I believe that we'll be able to gain one or two things that can help us in our future research. So I'll just call on Ms. Festa, to give us to read the biosketch of the presenter to us. Ms. Festa, over to you.
Good afternoon, everyone. Can you hear me?
Yes, you're audible. Yeah.
All right. I'm sorry about that.
Hello, Festa. Are you there?
Yeah, I'm with you. Yes.
Yes. Can we check?
I'm starting now. The speaker had his PhD from the University of Ibadan with core expertise in stochastic analysis and its applications, quantum probability, quantum information and communication processes, quantum computing, finance, and computational mathematics. His doctoral research was a study on establishing existence results for a class of quantum stochastic differential inclusions, which is the QSDI, which employs the strong operator topology generated by the strong family of semi-norm to investigate existence and convexified problem of a class of QSDI in a locally convex space of operator observables whose topology is generated by a strong family of semi-norm defined via the norm of the Fock space. He has presented his research at both local and international conferences. He was awarded an African Hero and Outstanding Lecturer of the Year in 2023 by the Global Skill Hub, United Kingdom. Thank you.
Okay. So I'll just introduce the lecturer to us, who is Dr. Dauda Alani Dikko, who is a lecturer from the Department of Mathematics at the University of Ibadan, the premier university in Nigeria. And in his talk, I will leave him to introduce us to this topic. And I think I just throw the baton to Dr. Dikko. Dr. Dikko, thank you very much for honoring our invitation.
Thank you for the invite. Thank you so much.
So I think
share my screen.
you can now share your screen.
Is it clear? Can you all see it? Am I audible?
Excellent. You're audible and you can
Yes.
see.
So I must first appreciate the organizers for this invite, and I must be sincere with you. When he gave me the invite, I was of the opinion that would this be a very ideal thing to give on an online talk because of the required basics to study this field. But I appreciate him for his encouragement, particularly when he mentioned the part of collaborations and people understanding what one is doing. I think it is worth it. So I thank you so much, Dr. Julius, for this invite. The second thing is to say that in the world is celebrating 100 years of quantum. And very many researches, talks in this year are given to commemorate the year. So for some of us, I know a larger part of this talk will be very new. So I might not be too keen on saying that I want to get to the end at all costs because I have a very bulky slide, but it's because I need to give some basis. So you have to just keep warning me when it is close to the time I should stop so that I don't spend too much time on some parts. So it is a good thing to see what we are doing here in Ibadan. I must first appreciate my teachers who started this area and who have been our motivator in this field. When people ask me, what do you do in mathematics? And I tell them, I just laugh that one day you'll see it when I give a talk. So it's an opportunity. A number of my students are also listening now. So it's a way of also teaching them. The title is Numerics of Quantum Stochastic Differential Equations and Inclusions. Numerics because we want to eventually consider the numerical analysis of the work which has been done in the field of quantum stochastic differential equations. Particularly, I am lucky to have been supervised by the authors who have done this work. And then it is also important to see that we can also build more on whatever has been done. Therefore, it is worthy to see that we can follow what I have here as a guide. In the abstract is already being read all over. Then I'll give the introduction. That introduction is much, but it goes into what we need to actually learn here. So first thing is this. I shall give a theoretical framework for the study of the Hudson-Parthasarathy Quantum Stochastic Calculus and as extended by Ekhaguere. Now, the Hudson-Parthasarathy Quantum Stochastic Calculus is a special kind of calculus that extends or that is built on the Ito stochastic calculus. We all know what differential equation does. We know their existence, there are solutions, and particularly we consider unique solutions. So we have studied this in our elementary classes, in the undergraduate class, and some in the postgraduate class. Furthermore, the extension of a noise influencing a system comes in, and then the Ito stochastic calculus became a very strong basis for studying systems that have noise embedded or built into them. Now, the extension to the quantum settings by Hudson and Parthasarathy we'll soon see is the introduction of operators from quantum mechanics, quantum field theory, and some other areas. And let me also say this, for you to study the kind of mathematics we do here, you need a number of fields. that you need to study in bits, or depending on what you meet along the line of your study. For example, you need to be strong with function analysis, operator algebra, probability theory, stochastic processes, quantum mechanics, representation theory, and some other allied areas. So when you meet what I'll be discussing, don't see it as anything too big. Yeah, because people have done it and we are also doing it. Now, I pick it from the study of stochastic differential equations, which is a central modeling in the field of mathematics, where you consider influences by what you call a noise. The noise is some form of some randomness that comes into what one is discussing. The equation 1 there is a general form of what a stochastic differential equation looks like. And you call it classical because you have not embedded the operator algebra or the kind of tools that makes it more rigorous in the study. Now, this same expression was extended by Hudson and Parthasarathy. These are two friends who did individual works in two ends of the world, one in UK, another in India, and met to see that what they were doing looks alike and they had to work together. So they came up with an expression of this form, which is known as quantum stochastic differential equation. Meanwhile, they are not the only one that have worked to give an expression for this kind of equation. In physics, it's a very common thing that you have people working with operators on differential equations. The particular thing about their own case is that this expression has the noise in what you call the boson-Fock space. The expression you will soon see. The boson-Fock space is a tensor product of some nth tensors of Hilbert spaces. The M you are seeing there is what we call a martingale. That's the way it is defined. The D kappa that you are seeing is what you call the number operator. The A dagger that you are seeing is the creation. The A that you are seeing, subscript G, is the annihilation. These are operators that is studied in quantum field theory. Okay. And if you are somebody familiar with areas like Lie groups and Lie algebra, we'll talk about the Lie bracket. Yeah, then you come to what we call the CCR, okay, canonical commutation relation. This is where these operators come in, and it guarantees that these operators are generally not commutative. Unlike this classical case, where our values are random variables and you can consider them as commutative cases. In this case, our operators are generally not commutative. Therefore, being operator valued, the name quantum comes in. Now, you will see in this page that the basic tools, which is the term, is being explained here. Okay, that QSDEs, they allow for formulation of stochastic models in a non-commutative, or you call it quantum framework, where random variables are replaced by operator valued, and then this approach extends the general probability theory that we know into quantum settings. It also enables us to see or have deeper understanding of stochastic processes of, quantum mechanics is a study of some micro particles, the photons, the phonons, the electrons, and their behaviors. Therefore, these studies are helped into applications in the field of quantum control, quantum open systems, quantum evolutions, and particularly quantum optics. A number of results that will come up or that is seen, generally, if you Google all this, you will see information about them. However, the fundamental tools that we use in mathematics, how have we also been able to place them in this field? And that is where the idea of doing some numerical approximation, creating numerical schemes, finding stable solutions, and whatever in this field, this is where it comes in. Therefore, despite the fact that you have some form of rigorous math, we still try to go close to what we have always known and see what we can do about it. Now, here I have mentioned that a notable property is that the general quantum representation reduces to the classical case, particularly when on the Fock space you deal with, you neglect the noises that the operators. I mean, therefore, you can work with, you can compare and see that this goes for real spaces. Now, having mentioned the origin a bit from what we have known, this might not be very familiar depending on how much we have studied. Ekhaguere is an emeritus professor here in Ibadan, created, or let me say, formulated an extension of the Hudson and Parthasarathy calculus on the boson space. And then he introduced a number of operators. He has the paper in 2007 where he showed 7 operators that can work in this field. One of the operators is what he used in the 1992 paper. In the 1992 paper, he reformulated an equivalent form that looks like a differential form, which is given by my equation 3 here, such that this differential form is a sesquilinear form. If you look at the references that was given in the abstract, one is major paper is there as one, and you will see these expressions there. Okay. Now, this is called a non-classical ordinary differential equation. You can see the movement. What we have always known, we have always done in school, in the classes, I mean, general ODEs, in whichever form, okay, can now be seen differently based on the operator valued form as a non-classical type. Now, all these have a base that makes it defined, and that is the density defined linear operator acting on the test operator of 2 or more Hilbert spaces. And in this case, it is called the boson-Fock space, which contains symmetric Hilbert spaces. Now, this equivalent form by Ekhaguere has facilitated a better understanding of what we know in the field of quantum stochastic differential equation. So it provides a pathway to, be able to do some form of numerical methods. Now, such numerical methods have been treated and worked on by my own mentor, my own supervisor, Professor Ayoola, here in Ibadan also. He has done works on the Lagrangian quadrature, on linear multisteps, and other numerical methods. Okay, so by this talk, I shall be looking eventually at one of the methods because I know I don't have all the time. Now, this is the movement between, or the relation between classical and quantum. In classical probability space, just imagine it. I have a coin, I toss a coin, I create a sample space. This we have always done. Okay, our sample space is omega. Okay, we can generate a sigma algebra. Okay, that's the family of all possible subsets. Then we can create a filtration. That filtration gives us the information on that space. Okay, then we determine a measure. Because it's probability, the measure has to be, measure on mu has to be 1. Now, that's for the classical case, which we have always done. Now, for the general stochastic analysis or stochastic processes that we know, we work on an L2 that is defined on the space omega, sigma algebra, and mu. Then we have our sample space to be an Hilbert space. Then we define our Lebesgue measure and generate these algebras that comes with it, define the filtration as some form of von Neumann algebra. Then in the quantum case, we have our Hilbert space as our sample space, then a cyclic vector, which is a combination of Hilbert space. Then we define our algebra, a non-commutative von Neumann algebra, which is W-star algebra, and then we have our trace. This trace is what gives us the expectation. We can use the trace to also determine the variance. Two things that are very important in probability are those two things. So our trace are defined in some form that you can use that to determine, particularly in the case of a finite dimensional Hilbert space. So this is a table that shows the relationship between classical and quantum generalization. Now, that is one. The second thing, which is core, is the differential inclusions, because I mentioned in the title equations and inclusions. Okay, and I mentioned that one might need to learn so much. One of the areas you need to also see is this area that has to do with differential inclusions. What's a differential inclusion? Generally, we know what a differential equation is. An expression like I is well known to us, where we know the existence, results that we have, the piano's existence, all the general OD existence results, the ones that have to do with uniqueness, and other ones. Now, with that, we know how a system behaves. So many results are known. Any n-term ODE can be put in a first-order ODE, and you can do your mathematics with it. But in a case where you have an inclusion, what does it mean? The point is, at some point, you can have what you have as an admissible set of control, where you have your x prime of t to be equal to f of t, x of t, comma u, where u is the set of controls. Because of that set of controls, it can be written as my equation II. That is where inclusions come in. So inclusions have different names. You can call them multi-valued differential equations, discontinuous differential equations, and set-valued forms. Okay, this is also common in dynamic systems that have uncertainties. So it helps us to be able to see how we can embed this in what we do in stochastic. So we know now what an inclusion is. For an inclusion, the right-hand side is a set and not an equation where we can determine unique. So uniqueness becomes a thing of tough business that you have to do. So the ambiguity that comes with normal derivatives cannot follow now in inclusions. So it becomes a more difficult problem to solve. And inclusions can be seen in different areas, variational inequalities, control theory, game theory, physics, in a lot of areas. In fact, presently, there are so much that can be done. Now, we can write our inclusion like our first-order ODE, where we can look at an initial value problem. And the same way, we can generate a Cauchy problem. And this Cauchy problem is what we now generalize and can be done with our quantum form. This is the work Ekhaguere has done. In his 1992 paper, he was able to show existence results for a quantum stochastic differential inclusions, whereby you have the set-valued forms to have sesquilinear forms. All these are in his paper. Now, this has been shown by Ogudero and Ayoola in 2010 that, they can be applied in control. And then he also mentioned it there in his paper that this can occur as regularization of quantum stochastic differential equations. Now, there are a number of things that has to follow. I'll be fast now. Here, this is the Hilbert space that discusses the boson-Fock space. It's a direct sum coupled with a tensor product. Now, the EF you are seeing there is what you call the exponential vectors, because the exponential vectors is what our tools in our numerical schemes would be. Okay, there is a lot of mathematics to be known about this also. Now, these exponential vectors, you can call them coherent vectors. They are actually dense in the Fock space. So, you know what that dense means? So, they have these following properties: the span, okay, is dense in the Fock space, then the product, the inner product of exponential vectors are written that way, then you can have a linear dependent of the exponential vectors in the Fock space. And my gamma h is the Fock space. Then you have the direct sum, then you can write a factorization, as you can see there. Now, this is the domain where this will work. That to each pair, okay, D, H, consisting of pre-Hilbert space D and a completion H, then we can write this set of linear maps, okay, such that the property of X star being the adjoint of X from the Hilbert space, okay, contains the domain D. So this makes what we are doing defined. So the problem about the domain problems will be solved with this. And that is where our domain of operation lies. Now, Ekhaguere was able to also show a space. That space is this, okay? This space contains, you see the domain is D with the algebraic tensor E. D is a pre-Hilbert space and its completion is in R, while E is an exponential vector which is dense in the Fock space, gamma 2 of R. Now, with the tensor product, you can look at it in the range 0 to T and the range T to infinity. That is what the AT and the H subscript and the A with the upper subscript does. Okay, so that you can, as a process, you can define a process on them and work with it. Now, we need this family of seminom because the space we are working with here are actually locally convex spaces. So with this, I mentioned earlier that in 2007, Ekhaguere defined some 7 operators that works in this space. So one of them is what is used in his 1992 paper, which is what is rigorously used to establish new results. Now, that same seminom, the weak family of seminom, is what we use, what Ayoola used, and what some of us have also used in establishing some of our results. Now, the topology defined on it is this, for set valued case now, you need to know what is the notion of distance. Okay, neta psi is just to say, because by the time you talk about its linear form, then what we are working on sits in C. Therefore, we can now look at the concept of distance, the infimum between X and Y for all Y in N, where N is a closed value in the space A. Okay, then you can look at that as a point to set. Then you can look at the set to set distance. Then you can look at the maximum of the distance between any two sets, no matter how you change it. Okay, that's what this one does. And when you restrict it to C, then you can take an absolute value and determine the distance, just like what is given here. So these two follow themselves. So you can use that to do some topological computation. So now you have the boson quantum stochastic integration. Here, it was able to give us definition for adaptedness, so that we can use that to generate information. And here, he brought what works like a major theoretic settings in this space that we're working on. These are the measurable locally bounded functions and the measurable locally bounded endomorphisms, okay? And this is how it is defined. Now, these operators here, they actually maps, okay, are brought in from the quantum field theory. In fact, Hudson and Parthasarathy also defined them, but they give us they help us to define the processes that we are dealing with. For example, the annihilation AF of T as a process is given as AF with the chi 0T. Then the creation is also defined, and the gauge or the number process, they are defined analogously as processes. That is what you see on this page. Now, this is to show how the operation is. If you look at where it is given as RT in bracket C tensor E alpha, the behavior of that tensor product goes that way. And that is what we are being guided with. Now, this is the adapted stochastic process of the Hudson-Parthasarathy. This is the way it is defined. And you will see the processes we are talking about are given, where you have Pt gamma pi minus, at t and at tn. That is to say the processes with time changing. Okay, so that is how that is also defined. All this can also be seen in the, but there are more results that work with them. Then the integral of the Hudson-Parthasarathy is what is given as MP. So for every integral operator, you have a differential version, and that is the differential version given as the DMT. Okay, now this is what was worked on by Ekhaguere with multi-value processes. These definitions here is just a guide on how the multi-value processes are defined. Okay, and multi-valued form, let me give you a very simple way to see it. For in probability, we can determine all possible, like a Zimmer algebra, all possible elements of a family of sets. You can determine, for example, if a set contains two elements, okay, the total possible element it can contain is 2 raised to the power 2. If it contains 3, then you have 2 raised to the power 3. If it contains 10, then you have 2 raised to the power 10 as the total number of possible subset that you can have. That is exactly what this is trying to generate. From classical to quantum, for any space you deal with, you can take all possible values of subclass of your space. And these multi-valued forms are defined this way, and then extended in the form of a locally Lebesgue multi-valued stochastic processes. And that's what it means. When you used to say LP log, is to say locally P times integrable space A, which is a multi-value process. So with that, you can follow up the reading, because most of the notations that are given here has their definition based on how it makes it work. So it's important to know them. Now, what I have on this page is how you define your set valued form. On the left-hand side, you have the integral of phi s of x of s with the martingale DMS, okay, defined as a set. On the right-hand side, you have a set valued form. You have everything as set. So which means that whether I am taking, my martingales are my noises, okay? So any of them I take come together in this family, okay? And then the integral operator we are talking about is the last line you are seeing there. This is the Ekhaguere formulation that we deal with. The expression is in this form. You can see that our x of t is an element of the way I define an inclusion. In fact, that is the reason we have to define that inclusion. So you can see that the kind of integral we are dealing with here is not an equation, but an inclusion. Now, this can be written as a differential form, okay? Generally, every integral form has a differential form then, with the initial condition. And then a solution, in this case, will be looked at as a weakly absolutely continuous stochastic process. The solution itself is a process. And you will observe that we did not use P, Q, V, U like the Hudson and Parthasarathy. We used coefficients that themselves are maps. And these maps are defined this way. Okay, this one is just to talk about the closed convex hull. Yes, this is how the maps are defined. Our E takes value from 0t cross A to 2. You can see here we have our power set. Okay, so this is the idea of what the set value representation is talking about, and all other ones are defined analogously. Now, this inclusion is what you can see here on this page. What I have is the differential form, which was shown to be equivalent to the second one here. The first one that you are seeing is a differential inclusion. Now, with some mathematics that has been done, we were able to see that the first inclusion is equivalent to the second inclusion. I want to call your attention to something very particular. When we started with the ODEs, we were writing x prime at t. Is that not it? We are writing x prime at t, okay, to be equals to f of t, comma, x of t. Now, in this case now, okay, this was f of t, comma, x of t. If you compare what we have here with the sesquilinear form, this equivalent form, this is classical, and here, this is quantum. So it helps us to make work easy for us, for ourselves, to generate new results. You will soon see part of what I'm saying now. Now, this is the map that describes the... I want to also say something here, that the way the coefficient behaves determine the inclusion. What I mean is this. You see, in this line or this direction of research, we have so many cases. Our E, S, X of S, our F, our G, let me just call it EFGH. Our EFGH can be discontinuous. Okay? And that is where the results about discontinuity of these same inclusions come in. In fact, the works of Ogudiran and some of us also worked that direction, and Ayoola, are shown that you have the discontinuous differential inclusions. Okay? There are also other authors, but I don't want to go too much in those, since I'm not dealing with just this alone. Now, coming to what we are here for. Everybody has a background idea now. When I write expressions, you can picture it from the explanations I've given. We know this very well. In our Simpson's rule, we know that we are dealing with ODEs, which are initial value problems, okay? Then we can look at intervals, the grid points, and then we can write some form of expressions that gives us what the Simpson's rules obey. So you have the 1/3, you have the 3/8, and I mean, depending on how we want to look at the problem we want to solve and which one gives us a better accuracy. I mean, so this is what we know so well. This is an example of a numerical scheme for the Simpson's rule, and it follows this. Now, where I'm really going is now, Adeyeye, who also worked with Ayoola. All these are classical, we know them. Okay? Now, worked on some extension of Ayoola's work. Because for me, when I teach numerical analysis, the first thing I do is, when I teach numerical methods, this is one of the methods I teach at the maybe like 200 level, 300 level. And engineering student and statistics, I mean, they need to understand some of these tools. Okay, so this, I mean, guides us on checking for a number of things, how differential equations behave, how to get the best method to use when you are solving a problem. Now, if you look at what is on the screen now, you have a differential form, which is a quantum stochastic differential equation as established by Ekhaguere. Now, look at where I started from. This equivalent form has the way we can write this as an integral form. I mean, this we have known. If you observe, you will see this here. You know this already. You see this here and this to be a form like what our classical differential equation is. What I have here, this. And this is what I was trying to show when I was writing at the other time. So therefore, it makes it easy for us to say, can we generate a scheme and for the C rule that we know in the quantum settings? Okay, these ones we know them. Therefore, Adeyeye was able to generate some results that can give solutions to such differential equations. Mind you, not inclusion now, equations. You know, the equation is without control. It is the inclusion that has the control, explicit control, called the adductive ones. So therefore, what he was able to do was to generate schemes for the equations. If you look at this is almost similar to what we have in the classical case. If you look at this, what I have here, my xi plus 1, given as xi minus 1, h over 3, f of all the functions, and 4h over 3 and the other part with their initial conditions. So this scheme is what Adeyeye was able to re-express, giving some results, and following basic mathematical principles, okay? Replacing terms, substituting terms for themselves as it is defined. If you look at this, in the earlier part here, you can see our x prime. You can see this. Now go back up to the classical case. In the classical case, you have the same expression. You can see it here. Because originally our classical form is actually telling us that our x prime is f of tx. Therefore, rewriting this way, was able to now create this scheme, okay, for the quantum stochastic differential equation as the computational algorithms. There were some preliminary results which he used, and here, I mean, the normal iteration process that we have always done was able to now use to get what I have here is, look at it, x of 2. I mean, if I have x2, I can determine x0 and x1. Although in the quantum settings, if I have x3, to compute x3, I can use what? x1 and x2, just like our normal iteration. And with this, I mean, it was able to expand, simplify, create a real part and an imaginary part. Why? Because our sextilinear form now sits in C. Our PT of x of t is now complex. So, I mean, then he used this result. I mean, I'm stating the result without proof, okay? And the second result, it was able to employ them in the theorem where you eventually show convergence of the exact solution. Given this Lipschitz function or Lipschitz constant, as you can see it has to be absolute value because of the complex, because, you know, k in eta psi is not a complex number, okay? So this theorem guides us that this solution exists, and then we call it convergence theorem. This is the process. It's in the paper, although here it is more explicit, it's more open for understanding. You start with taking the difference between the approximate and exact solution. Then you bring it into a form of, bring the integral, Then you introduce our numerical scheme, for what? For our PT of x. Remember, this is our error term. Therefore, he was able to move this and eventually show that this holds, and the bounds, when you introduce it, you compute and get what eventually our error can be. And with that, a check for stability did the error term, and that was how the first results on the Simpsons rule came about. Now, in the second case, because initially I had in mind that I might not be able to get to the Lagrangian case, but for the Lagrangian quadrature form, just like the normal Lagrange formula that we have always used, Ayoola generated a quantum version in 2002. In fact, this was a major result. he used to tell us that this result took 3 years before it was published to make one see how some of these our predecessors have worked so hard to ensure that their results get known and are established facts. These are the bases. You try to look at our PT of x to be, a continuous function. You know, continuity is general and is very essential in what we do. Whatever we do in math, if you don't have a continuous function, you can't generate a solution. And that is exactly what this is talking about. Now, if you look at, with this primary assumption, it was able to write an expression of this form with our Lagrange basis. This we are familiar with, in fact, from undergraduate level, okay? You know, if you use x, you try to determine your value of x, given that you know some of the nodal points, and then you can generate as much result as you want with that. Therefore, determine the L with this expression, where our Tn of t are the intervals, like you always know. Then our basis function can take value 0 or 1, you know. This is to say, like what we do in measure theory. Okay. Now, then our differential coefficients our coordinator coefficient can be written in this form, that you take the interpolant such that you have the nodes. Okay. Then our U from here, just like we have our intervals, when we pick the nodal point, you can also write a linear transformation in such a way that you can determine what U value would be, and then this becomes what is used as tools in the Lagrangian form. So a general expression was also established. But in any case, he was also able to establish a numerical scheme using the Lagrange formulation that we know in the classical case. You can see that although the result here, I was not able to fix it the way I want. So, but you can look at the paper. If you look at the paper, which I refer to, you observe and see that it was able to determine some form of error. You define one global and the other one as local, and it was able to show the convergence also and how the solution comes in. I'm sorry that this is not coming the way I want. I don't know that this is what happened to it. I'm just saying it this way because I just added it today. So it was able to show the exact and the exact solution and the computed values. I'm sorry, I don't know how this, maybe my system, but it has turned it upside down. I don't know. Yeah, with the lot and cockatiel. It's okay, but in any case, this is let me see. Okay, I think I was the one that caused it. I'm sorry. I was the one that clicked or touched the rotation. It's a touch screen, so it touched the rotation. So you can see what I was trying to express here. So you defined S of Tp as the exact solution at T equals Tp and the approximate solution as X of P. Then at X of T, the approximate value at the other point. Yeah, so the global error is defined as this. You see, the neutral side that is attached is only to help us know that this thing sits in a complex field using the weak operator on a locally convex space. So this deviation leaves the general Banach space that we know. In Banach space settings, you use just the norm. And that is where the difficulty level of these things are, because you need to know when these conditions are satisfied and this result hold. Okay, so that's exactly what you see. Our D tensor here is our domain. I've defined it. D, okay, is the pre-Hilbert space, while E is the exponential vector. So every neta and psi that you pick will have like an A tensor E of maybe R. This is the way each element of this would look like. I mean, if you pick a psi also, psi would also be given as maybe B tensor maybe E of maybe H. Okay, so all these hold in the quantum setting. So this is what was done in this work. He later defined the global error bound, and he was able to show with examples using the exponential vectors. I mean, because every exponential vector will give you a value at the end of the day, but it's an exponential vector on an element of the Hilbert space. So this is the idea in the papers which I have attached to the work as described in the abstract. And like I said, they are not new results, but to help us create a familiarity with this field. Now, I just pointed some things out here that I've only shown rudimentary knowledge, which is required for the study of quantum stochastic differential equations and inclusions. And some of the numerical schemes which has been shown were described and how some of them were done. I've tried to be as close as the classical case, which everybody knows. The only thing you need to know very well is the foundational structure, which I also tried a bit to explain, but I can't do that obviously, even if you give me 2 hours, because each of the definitions that is given with the annotations has to be explained. So I now mentioned here that, okay, the studies, I mean, is still wide open. We need to look at, like I worked with the strong topology in my Ph.D. thesis. I have not even shown what results of strong topologies here. So it is still wide open. We can still work on whether their properties, their numerical values, their numerical schemes, their analysis. I mean, I'm sorry, this should be strong and not string. Okay. Then the applications in these settings, the way it is described and defined here, we need people to come and work with us. Thank you for your rapt attention. These are some of the references. In the first few references you can see, these are the works of my predecessors, I mean, my teachers, and they are published in very high quality journals and best rated journals in the world. These are some of the references which also they used in some of the work which I also have also used. Then some other references, particularly Fagnola worked with in the Hudson-Parthasarathy settings, and this is the main Hudson-Parthasarathy paper which started what we do. I mean, the quantum method formula and stochastic evolution. It's a very, 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 very strong paper. Okay. Then okay, the paper of Ogudero, which shows applications. Then also my own some of my own works that have been done in the recent past, which have been published. I mean, also published in very good outlets. So this is all I have for us. Thank you so much for listening. I appreciate your time. Thank you. Yeah, if I have questions, thank you.
Thank you very much, Dr. Dikko. I want to really appreciate you and thank you, for trying to, explain and trying to create a soft landing for us to understand the connection between differential equations, differential inclusions, and also the quantum stochastic differential equation. I must thank you very much for your time and the way you're trying to break things. I know if you had more time, you'd have been able to actually break all these things very, very well, for us to understand. But one takeaway I want anybody to take from here is, this quantum field is very, very is an area that is not too explored amongst us here. But at least if you can understand this connection between what we already know, which is the differential equation, that is what everybody does, if you can understand the connection between them, then you can, I believe that is something that the students here can take up challenges and be able to explore new results and, you know, collaborate or meet up with Dr. Dikko to mentor you in this field. And also, one thing I would have appreciated, which I know that for some of the students that are here, I know, you know, they would have appreciated if they had seen like a numerical example, you know, for them to see, you know, some plots or something. But I know that there's no time. There's, you know, you were limited to, you know, there are a lot of things you still wanted to show that you were not able to show. And I want to say, I want to thank you very much, Dr. Dikko, for giving us this talk. And now I just go to some very important discussion. Let us just take some questions, observations, and comments on this topic. So if you have questions, please just use the React, you know, just raise up your hands and I will call you. Please don't interject somebody. Just raise up your hand. I will see your hands on the participation what they call it box there, and I will call you. Who is Professor Kolawole Ijadunola? Please, can you go ahead with your question?
Okay, thank you very much. Can you hear me?
Yeah, we can hear you. Can hear you loud and clear.
Thank you very much. First and foremost, I want to appreciate the presenter, Dr. Dikko, for this talk given to us. And as the moderator have rightly said, in the nearest future, maybe in another presentation, I would so much love it if our facilitator, our presenter can give us more examples on the application of this area. Even though we are a little familiar with some papers in this area, but the application of this work will be much more helpful for those people that are coming behind to be more interested in this area. If you look at this area, very few people are into it. But for us and many others to follow, we love it and I also appreciate it if we can have more application and examples on this in this area. Once again, I want to appreciate the presenter. May God continue to increase his knowledge in this area. Thank you and God bless.
Thank you. Professor Solomon Ojogbo.
All right.
Solomon.
Thank you very much, moderator. Thank you, the presenter, Dr. Dikko. Actually, my questions are two, although one has been asked by the moderator and also Professor Kolawole. So the next question I'd like to add to that is with regards to the scheme. You know, we as numerical analysts, we tend to use some set of softwares to develop our scheme and attain our numerical solution. So I don't know if there is an available scheme that if one wants to build on this work to have it developed from it, or is there a personal contact that we need to get through to Dr. Dikko on that? I don't know. So my two questions is one, with regards to the numerical tables, we have used two functions. You use the Lagrange and then you use the Simpson's rule as your scheme. So can we have sort of a table presentations to compare our numerical solutions to existing on this work that you have presented, and then if we can have a scheme such that we can still develop on it to have our numerical solutions that may be better than what we have currently. Thank you very much.
Okay, can I answer?
Any other question? Any other question so that Dr. Dikko can just answer everything together? Any other question? Okay, Dr. Dikko, you have the floor.
Well, I appreciate everybody's comment. I am also very happy to be able to present this to us because sincerely, if you see the way I've mixed all these things up and you go to those papers that I referred to, or any of these papers in this, I will give this to the organizers so that they can share for everyone. I mean, so you will discover that there is a lot more, much more than I have said. But I can assure you that with this little I have said, you have more confidence. I have seen people I gave these papers to, and they just look at it and return it to me. I mean, even outside this country, when I went to Germany, apart from those whose works are particularly related to this, even those whose work are related, they said, why did you have to go to this extent? And we also have these questions to our boss. Prof, why are we doing this kind of rigorous math? But I want to say this. In the present world of today, with quantum science and technology, there is no limit to knowledge. As I stand before you, I do things with IBM Quantum. I do this theory. I try to also do computational things. So that means that there is no, in fact, last week I was on Q Nigeria for, a talk like this, and I was telling them that most of the things that are used in the quantum information field, like in the computations, in the formulation of circuits for quantum computers, all these tools are the same. The Fock space is also being used. So this is key to every one of us. So particularly now to the questions you have asked. For example, you were asking about the numerical scheme. That's why I said it is not possible for me to put, even despite the fact I put 77 pages or 78 pages on this slide. You can see how I was able to just try to manipulate things to work. So the schemes are available in the paper. But recently, I am working with one of my students that is creating Python codes for each of this. This is being done presently in my institution. And we also did a systematic literature review, and we saw that, we can still write a new result on the trapezoidal rule, which also has been done. Okay, but we have not finished it. So these ones, we have Python codes that have been written to show the computations. The only thing one needs is to have understanding of the elements that will be used, not like random variables, not like numbers now. We are talking of the exponential vectors. So if that is what you want, we can always, you can always see that, and you can always contact us, for that, so we can look at it together based on what you know and what we know. We combine ideas, and that's how collaboration is built.
Thank you very much, Dr.
Also
Dikko.
on the current package, like I mentioned, Python. Then on applications, I hope I still have some time.
Yes, you can talk. Yes, please.
Yes, on applications. See, in the quantum world, there are no limits to applications. It is just that the direction that we have handled, that we have held, is not seeing practical applications that are physical. In mathematics, you create mathematics as application for mathematics. You create mathematics as application for other fields. You create mathematics for theory itself. So these are possible areas of application that we can, mention. Okay. Now, for applications that I have known, that I have seen, that I have read, if you go to authors like Alberto Baccelli, John Goff, Andreas Bukas, Akadi, there are so many authors that have shown clear applications of the Hudson-Parthasarathy formulation. In fact, in MIT, they have labs. That's one of the unfortunate things we have in Nigeria. We don't have labs where we can test for some of these results. And that's why they keep taking us away. You see? If not, we have geniuses that have done great jobs here. So for applications, I can bet it to you, in quantum optics, quantum measurement, there are a lot of applications. But because I'm actually dealing with the Ekhaguere formulation, I didn't restrict myself to the Hudson-Parthasarathy case. If not, I could have pointed applications particularly that have been done by some authors. I know a number of authors, but maybe I can also add that to some of the list of references that people can see.
I will appreciate. Thank you. I appreciate it. Thank you.
I'll do that. So thank you, sir. Any other questions?
Okay, maybe Dr. Salah, Professor Salah. Can you quickly just take your questions and let's wrap it up? Professor Salah Adamu, are you still here with us?
Yes, I am. Good evening.
Yes,
Thank
please
you. Good
quickly.
evening.
Please, quickly, your
Yeah.
question, quickly, please.
Okay, actually, I do not really have a question. I want to commend the speaker. And secondly, the speaker has also guided me so much in the recent research we've been doing in this area. If time permits later in the future, I can come up with some examples. Well, someone was asking of numerical examples.
Yeah.
Actually, we have also started working on that. And soon we are going to be able to put up some presentations on that to show the numerical examples. It is easy to, the only challenge I think I keep having in this field is trying to model a physical problem to give us a QSD in the integral form. Now, when we have the QSD in that integral form where the presenter started from, using the Ekhaguere's results, moving from that integral form to the Cauchy equivalent is a straightforward thing. And once you get to the Cauchy equivalent, we've seen that we can now use even novel methods or more convergent numerical schemes to find solution in terms of the matrix elements that characterize that Cauchy equivalent. So maybe one of the time when we have chance, I'll be able to show some examples on that. Thank you.
Excellent.
Thank
Maybe you can
you,
put.
Dr. Adam. Yes, I'm happy about that. I never even knew he was online until he asked this question. He's
Okay.
also working in this field, and also he's rounding up his PhD here. I think before the middle of next year, we should be sure to celebrate him too. And he has also shown extension with the physics-informed neural network. So, in fact, he has shown a particular, maybe, I mean, like he said, he will still come and present too. He will show you the applications in the neural network field. I mean, in physics. So I'm happy that he's here. So that is one area of application of this class of QSDE that we are dealing with. Thank you.
Okay. Okay. So maybe I should just come in now, just to make this area attractive to people, and for people to actually appreciate this thing. I think I might give Dr. Salahu the opportunity to give the seminar for December. Will it be okay for you to do that?
Please, can it be in January?
In January, okay. In January, okay. I will keep you up for January. Now, let me just use opportunity to tell people at the chat box. If you check your chat box, you will see our website for this talk. You can visit there tomorrow for this talk will be there by tomorrow, so that you can watch it directly or download if you want to download directly from the website. And if you need resources and materials, if you want to join this cluster, you can fill a form on the website. You see a place where you can where you can join. Join now. It's not an association, please. It's just a place where that place is just for me to get records, so I can send you emails directly, for our meetings and for seminars and the materials. Because after this, what they call it, this talk now, I'm going to collect the material from Dr. Dikko and give like a statement of where you have links where you can download all the materials and where you can watch all the videos. So I need email address of people where I can send it to, because I don't want to create a WhatsApp group. There are so many WhatsApp groups everywhere. I don't want any WhatsApp group. I just want to deal with people directly to their emails. So if you click on that website, you see, and if you also want to give us a talk, there's a place where you click apply and give a talk. There's a place where you see join us. That join us is for where you can fill some things about your information, where we can reach out to you. Apply and give a talk is if you want to give us a talk, you can also click and fill the form so that you can give us a talk. And there are so many people here. I don't know if Dr. Adeyeye is still here. I've been trying to reach out to him all these years for him to give us a talk, but he has not been forthcoming. But I saw him here just now, and I think he has left. But if you want to give us a talk, we can create time for you to give us a talk, and also share your ideas to students so that people can also appreciate what you are doing.
Sorry, moderator. I intend to ask a brief question. Sorry, sir.
Yes, please.
A very quick one. Please, about the paper, this paper presented now, how do we get it?
Yes, so that's why I said you should fill there's a website. There's a website on the chat box. if you see the website on the chat box, you will see a place where it says join us. Okay, fill that form. We will extract your email address from there. From your email address, we send you a message tomorrow. Tomorrow morning, you get a message where you can get all the material, the videos, the slides, and everything.
All right, noted. Thank you.
Yes, thank you. Yes. All right, Dr. Dikko.
Thank you so much, sir.
I want to thank you so much for honoring our invitation, and I want to thank you very much for giving us a very wonderful and interesting talk. And I hope that students watching would have found some areas that they wish to collaborate with you. You may want to drop your email address on the chat box, maybe for under 10 seconds before I close it. Maybe people want to reach out to you. Dr. Dikko.
Yeah, I'll do that shortly.
Please quickly type your email on the chat box in case anybody wants to reach out to you, so that people can also create that network, because at least somebody can see you tomorrow somewhere in the US and say, I've met you before at when you gave us a talk somewhere.
Yeah.
And save this email address and try to reach out to him anytime. I want to appreciate everybody for coming for this seminar, and I wish you all very well in your research. And if you have questions, you have anybody you want us to invite, I'm still mentioning it again. If there's anybody, any field you are working on that is very challenging, that you find it very difficult, and you want us to invite somebody that is very notable in that, we have all it takes to invite anybody. So just send to us and we'll get across to the person. Thank you very much for coming, and I want to wish you well, and please enjoy the rest of the night. Bye-bye.
Thank you.
Thank you, sir.
Bye-bye.